Hello and welcome to the next lecture in Purification and Separation methodologies. In today's lecture, we will discuss about limitations of plate theory. As you could recall, we did plate theories exhaustively in the previous lecture, and then we would discuss rate theory in this lecture. During this discussion, we will conceptualize and define another term, HETP, which is height equivalent of a theoretical plate, and towards the end of this lecture we would be deriving a very important equation, which is Venn-Diameter equation. We discussed in the previous lecture about the plate theory and its significance as far as column efficiency was concerned. Nevertheless, there were certain limitations, there were certain things which plate theory could not explain. For example, plate theory could not explain the role of column geometry vis-a-vis column efficiency. Likewise, mobile phase velocity and its relationship towards column efficiency could not be established. Then properties of the column packing, such as particle size, pore size, etc., were also not really taken into consideration. And last but the most important, physical properties of the distribution system were not considered in the plate theory. What it means is, fundamentally, in plate theory we considered the equilibrium which is established, or the distribution equilibrium, which is established for the solute for its distribution into the mobile phase and the stationary phase. That was presumed to be very spontaneous and complete, and which may not be the case. Okay. So, because of those inherent limitations with plate theory, Venn-Diameter in 1956 brought about a new theory which was called rate theory or chromatographic rate theory. It is a more realistic picture. It talks about fundamentally about the mechanisms which underlie a separation process. So, if we could say that the plate theory explained the terms or the factors which were responsible for column efficiency, rate theory explained the underlying mechanisms for which those factors were able to hold sway. Now, this chromatographic rate theory primarily focuses on mechanisms for peak broadening. This term is not new to us, right? Peak broadening has also been taken up in the plate theory also. But rate theory talks about the mechanisms, and it talks about the mechanisms taking into consideration mobile phase velocity and its effects on peak broadening. Likewise, it talks about diffusion of solute, which is longitudinal diffusion, and its impact on peak broadening. And most importantly, it talks about availability of different paths for different solutes and its impact on the mechanism of peak broadening. To understand all these terms, let me try to introduce and conceptualize another term here, which is height equivalent of a theoretical plate, which is abbreviated as HETP, and it is denoted as H. Height equivalent of a theoretical plate it describes length of a column that corresponds to one theoretical plate. Now, this concept of theoretical plate we had understood in the previous lecture in great details. This number of theoretical plates given by n, I told you, is the smallest area in which equilibrium between of a solute between a mobile phase and the stationary phase exists, right. Now, height of a theoretical plate h is equal to L upon n. So, the total length of the column L, which is divided by one theoretical plate, would give you height of one theoretical plate. We have been familiar with this chromatogram for a long time. Assuming that a chromatographic peak would have a Gaussian shape which has a baseline width W, we are now going to explain and introduce another term which is primarily connected to the Gaussian shape of the curve, and that is the standard deviation. So, W can be equivalent to 4 times the standard deviation, as is shown here. W equals to 4 tau. This standard deviation tau is in the units of time. It is important for us to know because as I have told you, this chromatogram can also take a shape in the form of or a function of length, a function of time. So, we are not talking about the distance, we are explaining the standard deviation in the form of time. It can be related to the distance also. Let us see how. So, if standard deviation has to be evaluated in terms of distance, which is sigma, so it would be sigma equals to u times tau, where u represents average linear velocity of solutes. It is not very difficult to understand. Now, distance equals speed into time, right. So, the speed here is the average linear velocity of the solute, and tau is the corresponding time of the existence of this peak. Hence, the standard deviation in terms of distance would be u times tau, and I want you to keep this equation in mind. We will use it in the next slide. Now, when we talk of this average linear velocity of solutes, which is u, it is equal to distance travelled by solute in a column upon time spent by solute in a column. That is a direct relationship, which means this u should be equal to the length of the column, which would be the distance travelled by solute, right, which is given by L, upon retention time Tr of the solute. So, that Tr corresponds to time spent by solute in a column. So, we have another relationship here, u equals L upon Tr. Now, as we saw in the previous slide, W equals to 4 tau and tau equals to sigma upon u, that we saw in the previous slide. So, it means W equals to 4 sigma upon u, and if you bring in this value of u from this equation, it becomes W equals to 4 sigma Tr upon L. It is a simple derivation, we are just putting in the values we saw in the previous slide and this slide. So, let us take it further. We had seen in the previous lecture that number of plates is equal to 16 times Tr upon W whole square, and now we have seen in the last slide W is equal to 4 sigma Tr upon L. So, we can put this value of W here in this equation for number of plates. What do we get? If we do that, we would get 16 Tr square L square upon 16 sigma square Tr square. Now, some of the terms, this 16 and Tr will strike out, and what you are left with is n equals to L square upon sigma square, this value here. Now, what is the significance of this equation? We have seen that height corresponding to a theoretical plate H is equal to length of the column upon n, which is number of theoretical plates. Now, if you put this value of n here and substitute into this equation, what do we get? We get H equals to sigma square upon L. What does that mean? That means HETP, which is height equivalent of a theoretical plate, or H, it is defined as variance per unit length of a column. The sigma square is a statistical property. It is called variance, and it is associated every time with a Gaussian shaped curve or a Gaussian shaped peak. So, another very important point to note here is, when we were talking about n in the plate theory and in the previous lectures, n was dependent upon L, whereas this height corresponding to one theoretical plate, and we have obtained this equation, in this height is independent on column length. It is variance, this factor sigma square, on which height actually depends. What is the other significance of height corresponding to one theoretical plate? If height corresponding to one theoretical plate is less in a chromatographic experiment, it means variance, which is that sigma square, of a peak would also be less. Now, when we talk of variance of a peak, it means variance from what? So, it means variance from an ideal behavior. Remember what we saw in some of the previous lectures. The ideal behavior is when a peak can be obtained as a square shaped that square line rather than a Gaussian shaped curve, right. So, that variance would also be less if height corresponding to one plate is less, which would mean that column efficiency of such a chromatographic experiment would be high. So, that is how height equivalent to a theoretical plate is related to column efficiency. It can be seen in these two chromatograms shown below, and out of these two chromatograms you could easily note that one having a large variance, large sigma square value, is the one which is having low column efficiency, and the other one having a small sigma square value is the one having high column efficiency. Now, how do we get a quantitative relationship for height equivalent to theoretical plate with peak broadening effect? That is where the rate theory comes into picture. Now, rate theory tells us that there are different mechanisms which are underlying for this phenomena of peak broadening, and all of these phenomena can be actually related to height of a theoretical plate. One such phenomena is eddy diffusion or multiple paths. We will see these phenomena in great detail. For the time being, I just want you to keep these phenomena in mind. The second phenomena is longitudinal diffusion. The third phenomena is mass transfer in the stationary phase, and the fourth phenomena is mass transfer in the mobile phase. These last two phenomena, mass transfer in stationary phase and mass transfer in the mobile phase, actually talk about the equilibrium, that distribution equilibrium of a solute in the mobile phase and the stationary phase. Now, all these four phenomena or all these four mechanisms, they influence peak broadening, and hence they influence peak height, which is h. Another very important point to note is all of these phenomena, they work independently of each other. So, it means every phenomena will influence height, and the overall height would actually be a summative effect of all these individual phenomena, right. That I want you to bear in mind. Let us try to understand these phenomena or these mechanisms one by one. The first is eddy diffusion. What is eddy diffusion? Eddy diffusion talks about that solute molecules would have a tendency to follow multiple paths which may differ in length. What does it mean? Look at this picture here. We can assume this as a column, a packed column, and all these black dots are stationary phase particles. These are packed inside this column. Now, if you load a solute to it, let us assume that this solute contains only one type of material, okay? Only one material. Now, there would be n molecules of this one material here. Each molecule of this material, of this solute, would have to traverse a path from this end of the column to this end of the column. Now, interestingly, by virtue of packing of the stationary material, you could have, or this solute could have, options of various paths to pick from. For example, 3 such exemplary paths are shown here in green, blue and red. What is the difference between these 3 paths? The obvious difference between these 3 paths is, for example, this green path seems to be the shortest path available for a solute molecule, whereas this red path seems to be the longest one for the solute particle, and this blue one is somewhere in between. Now, let us assume there are 3 particles, 3 molecules of the same kind, of the same solute. One takes up this green path, another one takes up this blue path, and the last one takes up this red path. What would be the impact on the chromatogram? Each of them would reach the chromatogram or the detector at a different time. It has nothing to do with the property of a solute. It has to do with the type, the packing of the stationary phase, and it is the different paths available by virtue of the stationary phase. Now, that would introduce peak broadening into a chromatographic column or a chromatographic experiment. So, the longer path arrives at the end of the column and the shortest one would arrive at the earliest. So, eddy diffusion talks about peak broadening process due to presence of multiple flow paths through a column. How do we circumvent this? To know that, we need to know what causes eddy diffusion. There are 2 factors. First factor is packing consistency. The packing material in a stationary phase is not uniformly packed, right. There are very small subtle non-uniformities which are enough to create such different paths. And the second is, whenever we pack a stationary phase with particles, we talk of average diameter of the stationary phase particles. What it means? That the actual diameter of particles in fact vary. It is different from the average diameter. It could be more, some particles would have a little more diameter and some would have little less diameter from the average diameter. It means the particles are of different sizes inside the stationary phase, and that creates this inhomogeneity in packing and creating those multiple paths. Now, this eddy diffusion and its contribution to plate height is given by this expression. It is equal to 2 lambda dp, where this dp is average diameter of particulate packing material and lambda is a constant which accounts for consistency of the packing. In case we would like to minimize eddy diffusion and create a very well separated and resolved peak, what we need to do is to decrease dp, which we can do by taking small range of stationary phase particles, it is a small diameter particles, and by taking well packed column, by which we minimize this second constant term, this lambda here. And if we do that, HETP would be less, which means the column efficiency would be high. So, the last point about eddy diffusion is, understand that this term is related to all these 2 factors which are constant for a particular column. So, it means the contribution of eddy diffusion towards plate height in terms of average linear velocity is going to be independent. It means this HETP is going to be independent of average linear velocity u, and if we plot a graph between HETP versus u, it will show this independent relationship of average linear velocity and the height which is due to eddy diffusion. This brings into the second aspect which governs height of a theoretical plate. This factor is longitudinal diffusion. Now, what is longitudinal diffusion? Let us see. Longitudinal diffusion is peak broadening process due to diffusion of solute particles from areas of high concentration to low concentration. Now, this is something we have also seen in one of the lectures when I spoke about the principles of laminar flow. What happens in a laminar flow? Always in a laminar flow, one would notice the concentration of solute particles is always high in between the layers of the solvent or the mobile phase than the concentration which is present towards the edges on both the sides. Let us see what it does. So, it talks about the greatest scope of diffusion is along the axis of the flow, and that is why it is called longitudinal diffusion. This is the point I was trying to make. Look at this image here. According to basis of laminar flow, you have high concentration of solute particles in mobile phase towards the central part of this column here, and you would note that very small amount of concentration exists towards the edges of this column. Now, it creates an obvious concentration gradient across the length of this column. How that impacts the overall peak broadening? Now, because of this concentration gradient, at all times there would be some solute particles which would be moving from the central part towards the edges, and those particles would be lagging behind in when the solute is moving ahead. And because of this, you would note, as is shown in this peak, there is always a distribution of particles. You see most of the particles which are coming almost at one time here, and there are some particles which are on one side, they are coming slow, and there are some particles which have come forward. So, this is about longitudinal diffusion. How this contributes to the height of a theoretical plate is given by this expression. So, Hd equals to 2 gamma dm upon u, which is average velocity of the particles, and this gamma here is a constant which is again related to column packing. Dm is a solute's diffusion coefficient in the mobile phase, and u, as I told you, is an average linear velocity of the solute. So, in this case, if you note the contribution of this whole factor, which is longitudinal diffusion, towards this height of a theoretical plate is inversely proportional in terms of average linear velocity, right, which is obvious from this equation here. So, this longitudinal diffusion we can say is inversely proportional to average linear velocity. Now, if we similarly plot a graph of height corresponding to this longitudinal diffusion versus u, we would note this inverse relationship in the graph. This we have already seen. So, there is another thing which is to be noted in this particular equation. Height is equal to 2 gamma dm. It means it is directly proportional to this function dm, which is diffusion coefficient. Now, it is obvious that this diffusion coefficient would be high in gaseous states than in a liquid state, and you have gaseous state as a mobile phase in gas chromatography. So, it means in gas chromatographic systems, this dm tends to have a higher value in comparison to other chromatographic systems where mobile phase is liquid, and hence longitudinal diffusion is more of a serious problem in gas chromatography to be curtailed or to be handled in comparison to other chromatographic methods. Now, in order to circumvent this, what we need to do, since the relationship of height because of longitudinal diffusion is inversely proportional to average linear velocity, it means high the linear velocity, less would be longitudinal diffusion, and that would mean small would be your peak width and high would be column efficiency, right. But whenever I make these comments, you should always bear in mind that there is a limit to which we can increase all these factors. For example, if I say high linear velocity, you cannot increase linear velocity beyond a limit, right, and that we would see as the course progresses. This brings in to the last point for discussion, which impacts HETP, and this last point is nevertheless the most important point. It is mass transfer in the stationary and mobile phase. It talks about that a chromatographic separation occurs because solute move between stationary and mobile phase, right, that is obvious. This we have also seen. What plate theory assumed, in fact, this is one singular point where there is the major difference between plate theory and rate theory exists. What plate theory assumed that as soon as a solute particles they start to flow in the mobile phase, the equilibrium in every theoretical plate would start to establish, right, and it did not consider any time lag for that. It was spontaneous. Now, imagine that the chromatographic such separation occurs because solute will move between the stationary and mobile phase. It means solute will need some time to move to an interface between stationary and a mobile phase where actual separation and distribution would have to take place. So, what it means, the solute particle must first diffuse to the interface between the two phases, that is mobile phase and the stationary phase. Now, how that would result in peak broadening? It will result in peak broadening because the time required for a solute to move from mobile phase or stationary phase to the interface between the two phases would be different. It can be explained better once I show you the next slide. Let me take you to this slide. Now, in this slide, focus on this image, this figure here. This is one of the stationary phase particles here. Now, this stationary phase particles, it is made up of pores and interstices shown here. Now, within the pores or interstices, you would assume that solute particles would reside. Now, the mobile phase is here, the mobile phase is going across and over this stationary particle. Now, for an exchange, for any distribution of this solute particle between the stationary phase and the mobile phase to occur, this solute particles, let us say these two solute particles, both these solute particles would have to move to this interface here. This is the interface. Now, considering that this particle here resides very deeply into the pore, somewhere here, whereas for the other particle, this particle here, it resides almost at the interface. So, once this distribution will have to take place, both these particles will need to come to the interface, and there is certainly going to be a time lag. This particle will distribute faster, will move into the mobile phase faster, and likewise this particle will take some more time and it will start to lag behind. The same thing can be seen for the mobile phase. The solute particles which are very close to interface here in the mobile phase can easily distribute inside the cavity of a stationary phase particle, whereas those which are away from the interface will probably move ahead, and they will find slowly they will come to the interface and find some other solute, some other stationary particle and its interface. That whole phenomena creates peak broadening. All the particles are not moving at the same time, right, and this is the concept of mass transfer in stationary or mobile phase. As far its contribution to the height of a theoretical plate is concerned, both the stationary phase mass transfer and mobile phase mass transfer independently contribute to the height of a theoretical plate given by these two equations. This equation is height of a theoretical plate because of stationary mass transfer in stationary phase, and this equation is height of theoretical plate because of mass transfer in mobile phase. All the term used, this talk about dF talks about thickness of stationary phase, dC corresponds to column diameter, ds and dm is solutes diffusion coefficient in stationary and mobile phase, k is the capacity factor, dP is the average diameter of particle packing material. What is important for us to see though is that the contribution of this mass transfer in stationary or mobile phase is directly related or directly proportional to average linear velocity. Now, that means if we again plot a graph between height of a theoretical plate because of mass transfer in either stationary phase or mobile phase or combinedly in both the phases versus average linear velocity, we will always see a linear relationship, which means to circumvent this height component because of mass transfer, what we need to do? We would need to slow the flow rate. So, less is the flow rate, less would be the corresponding theoretical plate height. Again, this is with a word of caution, you cannot decrease the flow rate beyond a limit. Look at this slide. As I told you in the beginning, all these three factors, eddy diffusion, longitudinal diffusion and mass transfer, they contribute independently to the plate height. Now, what Van Demeter did, he summated all the three factors together and then brought about the overall height of a theoretical plate. So, to simplify it further, he replaced all these constant terms with these alphabets here. So, the first term, which is eddy diffusion, is replaced by A. The second term for longitudinal diffusion is replaced by B. So, it becomes B upon U, and the third term and the fourth terms are replaced by Cs and Cm respectively. So, these collectively become Cs plus Cm times U, and this is what we call Van Demeter equation. So, height of a theoretical plate equals A plus B upon U plus Cs plus Cm times U. Now, this is what we have seen, the individual impact of all these three factors on height of a theoretical plate. This was the impact of A, which was independent of U. This was the impact of B by U, which was inversely proportional, and this was the impact of Cu, which was linear. If we combine all the three, we get a graph of this hyperbola shape, and the dip of this hyperbola graph, this point, it corresponds to optimal linear velocity. So, this is the velocity one would look at to get the least value for height equivalent to theoretical plate, which would mean the most efficient column. Okay. So, this optimal linear velocity u opt, where HETP has a minimum value and the point of maximum column efficiency. Now, the last point to make here is how these factors influence the type of columns we use in chromatography. So, if one takes packed column, packed with a stationary phase, in such a column all the three factors, they contribute to band broadening. This factor A, this factor B and this factor C, all the three contribute. If one takes a capillary column, now in capillary column, as you can also visualize, there is no stationary phase, it is neither coated inside or whatever, the mobile phase is driven along the walls due to capillary action. So, in that case there is no stationary phase, and if there is no stationary phase, there is no eddy diffusion. So, this A term would become 0. Likewise, because there is no stationary term, the mass transfer also would become 0, and hence in capillary electrophoresis the only term to look into is this second term B upon U, and these columns should be construed as very efficient. Likewise, in open tubular columns wherein the stationary phase is coated in the inside walls of the column, in that case also, since nothing is packed, hence eddy diffusion term would be almost equivalent to 0, and hence these open tubular columns are also very efficient in comparison to the packed columns. So, with this we look forward to the next lecture, wherein I will be discussing about optimization of chromatographic separation, and then we would move on to gas chromatography. I look forward to have you in the next lecture. Thank you.